Good morning, everyone. Today we're gonna talk about last two sections of chapter four in the free body diagram, which we already worked on a little bit. So free body diagram is nothing but you shows every force is acting on the object that you're interested in, right? So for example, let's assume you have an elevator lifted by a cable, is moving upward and slowing. Here, two things, important word here, upward and slowing, right? Which is a correct free body diagram. Then your first step is identify all forces acting on the object, which is the elevator. So of course you have a tension upward and the weight acting downward, right? It's the same. And then now it says it's moving upward. That doesn't mean tension is always a greater. But you also have to focus on slowing. So let's assume an object is moving over and then slows down. So then there is a force acting downward to slow down this object, right? So then which force must be greater? So yes, the weight must be greater. So the answer is C, right? And then another example, a ball has been tossed straight up, which is the correct divided diagram. Just after the ball has left the hand. So then basically the ball is in the air. And then as we did in the chapter 2 and 3, the only force acting on the ball is the weight. Right? There's no other force. So the answer is B. Again, you have a ball hanging from the ceiling by a string, right? It's pulled back and released, which is the correct free body diagram. So then now you have a tension and the weight. That's the only force. A lot of students choose C or D or F because of the motion of the object. The motion of the ball is determined by the net force of the object, right? So don't this force, this is not a new force, but this is a sum of two vectors, okay, forces. So the answer is B, right? This is not a force, new force, right? So this is a kind of a result of these two forces. Same thing, a car is parked on a hill. So it's a parked, so that means it's a rest. So it means the net force is a zero. Again, normal force is acting perpendicular to the surface and the weight is acting downward, right? But if this is the only two force, you have a net force to the right, right? So then in order to make a net force zero, you should have another force acting to the left, right? So which is basically the friction force. So the answer is C. Similar thing, a car is towed to the right at constant speed. So important word here is a constant speed. If speed is constant, that means the velocity changes is zero, right? But the definition of acceleration is the delta v over delta t. So that means that this is zero as well. So in other words, constant speed means acceleration is zero. But acceleration zero is basically because of Newton's second law, if your acceleration zero, then force is zero, net force is zero as well, right? So these three things are equivalent. Constant velocity, constant speed equals A equals zero equals F is zero, right? So these three are always equivalent. So again, you have to make a net force zero. Again, normal force up, weight down, tension to the right, and then if this is all your net force, vertical forces will cancel out, but the horizontal force, tension, never gonna be canceled. So you need one force acting to the left, which is a friction force, and then the magnitude of all these are the same. So the answer is D. Again, the similar example we did, force is on an elevator. An elevator suspended by a cable. Again, we have a tension and weight acting up, down, right? And then now this time, this is a speeding up as it moves over. The situation is the same. You have an elevator or an object moving upward but speeding up. So that means which direction of force you have to apply. You gotta push from the bottom, right? Applying, forces, right? So the net force is upward. So in order to have a net force upward, the tension must be greater than the weight, right? So you have to, the length of this arrow must be greater than the length of this weight. And the skier example, same. This is a pretty similar with the car example we already talked about, right? So the tall rope pulls a skier up snow-covered hill at again constant speed. So then at the same time you can say, okay, my acceleration 0, and at the same time my net force is 0 as well, right? So then your force diagram, again normal force, weight, tension, and then this kinetic friction force, these all are must be balanced and 0, right? So vertical force, again, your W can be decomposed into two parts, right? Cancel, cancel. W is a horizontal component, and then this is a kinetic friction force, and tension will cancel out. And the last topic of chapter 4 is the Newton's third law. Newton's first law is inertia. Second law is F equal ma, and the third law is called action and reaction. But this is just about interacting, forces between two objects that you already know. So assuming you are, punch a wall with your fist, then what are you doing? You apply force on the wall, and at the same time the wall apply force on you, right? So basically it's kind of a force exchange between two objects, you and the wall. And the same thing happened, between this hammer and nail, right? So when you using hammer, right? So when you apply a force on the nail, what happened? Hammer applies a force on the nail, and then the nail applies the force on the hammer. But Newton's third law says the magnitude of the force, hammer on nail or nail on hammer, are the same. For example, if this is a 10 Newton, the other one is a 10 Newton as well. But the only difference is here is hammers apply force for this case on a nail to the right. So the direction is opposite. Nail applies force on the hammer to the left, right? Same thing, let's assume you have two objects. So object 1, A, for example, is a pushing object B. So they're called FA on B. And then A also will feel force by object B. That is called FB on A. Again, the thing is the force magnitude are the same. Direction is opposite, and we call it action and reaction pair. So Newton's third law summary, every force occurs. So here, every is important. There's no exception. Every force occurs as one member of an action and reaction pair of forces. In other words, force exists as a pair always. Okay. So the thing is magnitude equal direction opposite, right? For example, when you work, you apply force, you move forward because the surface of the earth actually applies force on you. And then at the same time, you apply force backward, on the earth. Same, car is moving forward, load is moving backwards. Okay. Same thing, rocket, right? Rocket is moving upward and the gas is moving backwards, right? So, for example, you have a Sarah and a skateboard, and the brother Jack, skateboard, and they push each other. What happened? They move backwards. This force Sarah on Jack. This force Jack on Sarah. The thing is, they have the equal force. right? And the same thing, you have a truck, and then you have a tiny mosquito hit each other, right? So the mosquito applies force on the truck at the same time. For truck applies the same amount of force on the mosquito. Magnitude the same, direction opposite. So the answer is a yes, C. So this is the last topic. One important thing of again the Newton's third law is they exchange the force, same magnitude and opposite direction. So you always have to identify two objects involved in the force first, and then first object apply force on second object, and the second object apply force on the first object. Let's see. Okay, so this chapter 4 is the introductory chapter for chapter 5, so you don't have a homework for chapter 5, okay? But after chapter 5, you will have the second exam, okay? Thank you. If you have any question, please again, must let me know. Thank you.